tactile and skin-like sensors require arrays of wired interconnects to detect human touch. For touch sensors on conventional electronic devices, standard manufacturing practices involve high-resolution printing, weaving, or semiconductor-based fabrication of wired grids. For these wired grids, the number of discrete sensing locations scales with the square of the number of wired leads connecting to the edges of the sensing surface. When the sensing area does not have overlapping wires, the number of discrete sensing locations scales linearly with the number of wired leads. This work presents a unique approach to the design, fabrication, and characterization of paper-based, skin-like sensors that use pattern-resistive networks for passive, scalable sensing with a reduced number of interconnects. We used laser-based ablation with an engraving system to etch patterns through the top conductive layer of metallized paper. The individual sensors consist of two fork-like interdigitated electrodes, one for excitation and one for ground. When making contact with the sensor, a finger acts as a conductive material with complex impedance to bridge the two electrodes. To characterize human electrode interactions with our paper-based devices, we performed measurements on an individual sensor. The figure reveals that the magnitude of the measured impedance decreased and the phase became less negative when a finger bridged the gap. The electrical networks are ladders in that each step consists of a main channel resistor and a capacitive sensor or button in series. These main channel resistors permit the measurement of distinct values of overall electrical impedance associated with the touch of each button in the passive network. To demonstrate the feasibility of using passive resistive networks to detect a touch at multiple locations, we fabricated a prototype with 14 buttons in a piece of A4-sized metallized paper. The excited lead of each progressing sensor taps into a section of the main channel resistor further down from the oscillating source. In the test, a user pressed each of the 14 buttons with a bare finger and repeated this process 5 times. As shown in the figures, the magnitudes of the touch sensors have distinct values at frequencies greater than 80 kHz or lower than 200 kHz. These results suggest that the design of a main channel resistor with section regions of resistance has significant effects on the frequency-dependent impedance of electrical networks for skin-like sensing. This figure illustrates the progressive steps in impedance as a user touched distinct buttons on a 14-button touchpad. The impedance of the 2-wire touchpad increased as the user progressed from button 1 to button 14 along the ladder-like layout of the touchpad. To test the suitability of a 14-button device for multiple users, 5 participants pressed each of the 14 buttons 3 times. While comparing the impedances of buttons touched by a single user with those touched by multiple users, we observed that the impedances of the fingers varied significantly between individuals. Therefore, it would be difficult to distinguish touch buttons for multiple users without adjusting the thresholds for the sensors. Since variability in impedances between users might undermine the use of passive resistive networks for large numbers of buttons, we designed a paper-based keyboard with electrical behavior decoupled from human impedance. To stabilize the electrical responses of each button, we used a highly conductive material, copper, to bridge the interdigitated electrodes on each button with the application of pressure from a finger. This video demonstrates that the 2-layer keyboard was stable and scalable. The passive resistive networks also have the potential to map other environmental factors spatially. In this demonstration, we designed a resistive network for mapping contact with dispensed droplets of water. Dispensed droplets of water showed a similar response to contact with a bare finger. When water fully wetted a button, the magnitude of impedance decreased to a stable value. Future Papertronic skin-like sensors might also be capable of monitoring bioelectrical signals, blood, or sweat. The final demonstration verified that the resistive networks were compatible with a modest wearable device that covered a curved surface. The simple layout of the circuits might contribute to the mass production of low-cost commercial human-machine interfaces and liquid leak detectors embedded in civil infrastructure.